Hey folks, in this video I'm going to introduce the constant acceleration equations, which are also known as the kinematics equations. These are four equations that you can use anytime you are working with problems involving constant acceleration. Most things in this physics course are constant acceleration until we get to the end of the course. So these are like mostly safe to use for now. The equations, three of them are in your equation sheet, and a fourth one is not, but it can be pretty useful to know that fourth one as long as you're careful to know when to use it. So this first part of the video is going to be showing you where they come from. The kinematics equations can be derived in a number of ways, and I'm going to use a velocity versus time graph to show you two of the equations. And then you'll have like enough to go on to see the connection. So we're going to start by imagining a velocity versus time graph for some object that has some initial velocity and accelerates to a final velocity in a certain amount of time t. And this is a really quick derivation because at time 0, this value is the initial velocity. I think I talked about it in another video, but the symbol for initial velocity can be VI or V0. We will specifically use V0 a lot in this class, and it represents the velocity at a time of 0, so whenever the problem or event starts. The end of the problem at time t, this is the final velocity. And again, in case I haven't talked about it, Vf and V are interchangeable. V naught or V0 represents the velocity at a time of 0, and then V represents the velocity at some time t. And what I'm going to do is we're going to fit this to the equation y equals mx plus b. So the value of y is whatever the velocity is. The value of x is whatever the time is. And b, the y-intercept, is v naught. The only thing missing here is m, which is the slope. And so from our previous lessons on graphs, we know that the slope of this particular line, so velocity versus time graph, is the acceleration. And so I'm going to put in an acceleration for that. So this really simple equation is essentially the equation of a straight line on a velocity versus time graph, and it is typically written v equals v naught plus a times t. So this is what I will probably refer to as the first kinematics equation. You can also refer to it as the velocity function. It is velocity as a function of time. And it's one of the most common kinematics equations that you will apply throughout the course. All right, so that's one of them. The other one is a more complicated derivation, and then I'll list out the other two equations that you can use. We actually start with the same graph. And instead of focusing on the equation of the line, we're going to focus on the other thing that we know about velocity versus time graphs, that the displacement using a velocity versus time graph is the area under the graph. And you can actually use this to get two different equations. I'm just going to show you the one. So again, we're going to start with like, okay, this object starts with an initial velocity. It ends with a final velocity, and it takes time t. We are now going to show the boundaries of this line for finding the area. So it goes from time of 0 to time t, and extends from the x-axis to the function itself, to the line itself. I'm going to add another line because it makes the derivation much easier. We are going to treat this as a rectangle and a triangle. So we'll start and we'll say, okay, this is area 1 and this is area 2. So the way this derivation goes is displacement is the area under the graph. And in order to do that, I'm going to have to do area of this first shape plus area of this second shape. Now, in the graph videos, you could have done like I didn't talk about it. I talked about it in class probably. You can do the area of a rectangle and a triangle or a trapezoid. Let's go with the rectangle triangle. So the area of a rectangle is base times height, and the area of a triangle is 1/2 base times height. So the rectangle is really easy. The base is time, and the height of the rectangle is the initial velocity. All right, so that's easy. There's really nothing to do with that one. That's going to stay as it is. So initial velocity times time. 1/2 base times height. Now this is the triangle. This gets a little trickier. The base is also time t, but the height is not the whole height of this. It's the height from here to here. Well, this line was at initial velocity, and the function is now at final velocity. So the height of the triangle is actually the final minus the initial velocity. Cool. That might jump out at you as change in velocity, but I'm going to leave it like that for a second so I can show you something else. If I look up at this first equation, I have v equals v naught plus at. I can subtract v naught from both sides, and I can get the relationship that v minus v naught is equal to at. So that comes from this first equation, and I know this to be true based on constant acceleration. So I'm going to perform a substitution because v minus v naught is what I have in parentheses, so I'm going to put at in there. Okay. So I'm going to clean this up a little bit, and I can write it as displacement equals initial velocity times time plus, and then this is 1/2 times t times at. So there's 2 times in there. So I'm going to write this as 1/2 at squared. And you might see me use this equation looking like this. Also, displacement is change in position. So a rearranged form that's in your equation sheet is x equals x naught plus v naught times time plus 1/2 at squared. This is something that I refer to as the second kinematics equation. It's also known as the position function. So the way it reads is the position of an object moving with constant acceleration is equal to its initial position plus its initial velocity times the amount of time it's moved plus 1/2 the acceleration times time squared. When you go learn calculus, you can see how these equations are related if you go take calculus. Otherwise, it'll just stay like this. Real quick, the other 2 equations. This is the third one that's in your equation sheet. This equation is one that does not have the time variable in it, and so that becomes very useful when you don't know how much time something's going to take, or you don't want to find the time. And the last one, which is not on your equation sheet at all, the reason it's not on the equation sheet is because the variable that's missing from this equation is acceleration. And so, in my opinion, it's not on the equation sheet because it's easy to forget that you have to verify constant acceleration first. So these are the 4 equations for kinematics, and in other videos we'll talk about how to use them, but now you have them. The big secret at the end of this video is that you don't need to know where these equations come from, but it's very, I think, useful to your brain to know that they come from graphs, and then once you get them from the graphs, algebraic manipulation is where you get the other ones.